Okay, in this lecture, we will take the ideas that we learned in the previous lecture and apply them to problems in static and dynamic equilibrium. And so you'll gain some practice in how to actually practically solve these types of problems. Okay, so when solving these problems, there is always a step-by-step process. First, we'll draw a free body diagram, and we had practice in the last lecture doing that. Then it's very important to define a coordinate system, that is some x and y axes for the motion. And then in each of these directions, x and y, we'll apply Newton's first and second laws to the motion and the forces from the free body diagram to determine the resulting accelerations and solve for unknowns. So for example, we'll look at two different situations. The first case is where the net force in a particular direction is 0, and that is to say that the acceleration here is 0, and that would imply that the velocity is a constant. Okay, so if the velocity is a constant, we'll call that a dynamic equilibrium. Okay, but if the velocity, if the constant is actually 0, that's a special case. When the velocity is 0, that's what we'll call static equilibrium. Okay, so that's for 0 acceleration. When the acceleration is non-zero in a particular direction, the net force, the sum of the forces, will actually equal mass times this acceleration. And this is a situation where we call non-equilibrium dynamics. Okay? And so you have to understand before you start the problem what type of problem it is that you're looking at. So it's important to sit down and think about that first. Okay, so let's begin with a simple problem. Here we have a 1.30 gram spider hanging from a thread, and a breeze is causing the spider to hang motionless with the thread making an angle of 35 degrees with respect to the vertical. Okay, so this is the vertical. The question asks, what is the tension in the thread and what is the force exerted by the breeze, the wind? Okay, so there's the force exerted by the wind in this direction, which is causing the spider to tilt this way. Okay, and then there's going to also be some tension in the thread. So the question is, what type of problem is this, first of all? And there are hints inside the question about this. The spider is hanging motionless, okay? So motionless means that the velocity of the spider is 0. And so this is a situation of static equilibrium. So with all problems, we start by drawing a free body diagram. And so I'll represent the spider as a dot, and then I'll apply the force of gravity downwards on the spider, mg. The tension in the thread points upwards along the thread, and it's represented by T, okay? And then the wind force is pointing to the left, and it is given by F sub W. And the tension force is at 35 degrees with respect to the vertical, okay? So again, if I were to draw here another parallel line, this is actually also 35 degrees by the parallel line theorem, okay? So now what we need to do is to solve for the Newton's laws in both the x and y directions. And first I should define what I mean by x and y. So I'll put up a coordinate system here where x is towards the right, and so right is positive, and y is up and down, and up is positive. Okay, so whichever way the arrow points in these coordinate systems is positive. Okay, so now we'd want to solve for the motion along x and for the motion along y. So starting along y, we get that the force along y consists of two parts, mg and the y component of tension. So if I write the y component of tension, Ty, and this is T, okay, and this is 35 degrees. So the y component of tension, well, Ty divided by T is just the cosine of 35 degrees, okay, by the cosine rule of adjacent over hypotenuse. So that means that Ty is T cosine 35 degrees, which I put here. It points upwards, so Ty is directed upwards, and so there's a plus sign here according to our coordinate system. And then to this we add the gravitational force, which is pointing downwards, so there's a minus sign, minus mg. And again, this is a situation where there's no acceleration and in fact no motion at all, so the sum of the forces along y is 0. Then I can isolate now and solve for t. T cos 35 degrees is equal to mg. Dividing both sides by cos 35, I get that the tension is mg divided by cos 35. And I plug in the numbers here for the 1.3 gram spider, and I get an overall tension of 0.0156 newtons. Now note that the size of the force is rather small, and that basically is because the mass here of the spider is actually in grams, right? So you have to be careful because 1 gram is actually 10 to the minus 3 kilograms, and so you have to do the conversion to kilograms before putting the mass into this formula. Another point to note here is a question about significant figures. So the answer in this question is to 3 significant figures. Okay, 1.56, there's 3 significant figures there. And the reason for that is because if you look at the question, all the numbers in this question, 1.30 and 35.0, are all to 3 significant figures. And so that gives you the hint as to what the question expects your answer, how many significant figures are expected to be kept in your answer. Okay, so that's for the y component. And so from the y component of motion, we get the tension. And now we want to figure out what the magnitude of the force exerted by the wind is. And so we can get that by solving the x component of the motion. So again, the x component of the motion consists of the wind, which is pointing to the left, so it comes in with a minus sign, and then the component of tension, Tx, okay? So Tx points to the right, and Tx over Ty is equal to the sine of 35 degrees because it's the opposite side divided by the hypotenuse. Okay, so Tx is equal to T sine 35 with a positive sign because it points to the right. And then I can solve this for Fw. Okay, Fw is T sine 35, and T, I know it's this value here, 0.0156 newtons, and so multiplying them out, I get that the force of the wind is 0.00892 newtons. Okay, good. Another example. Here I have a mass m suspended from 2 strings making angles of 60 degrees and 30 degrees with the horizontal. Okay, the tension in the shorter string is, and then is ... Okay, so the question asks for the tension in the shorter string. And let's just do this. Good. So I'll call this T1 and T2. And so I really want what T1 is. So is this a static equilibrium problem? Yes, because according to this diagram, the mass is motionless, okay? So this is again a static equilibrium problem. Okay, so I start off by drawing a free body diagram for the mass, and there'll be these two tensions, T1 pointing along the shorter string in this direction in blue, and T2 pointing along the longer string in this direction in red. And then there is also, acting on the mass, is the force of gravity, which points downwards. Then I want to create a coordinate system. And so again, I'll create a coordinate system here where to the right is positive along x and up is positive along y. Then I'll want to solve the motion in both the x direction and then separately in the y direction. And so I divide this line down here. This will be x and this will be in the y. So let's start in the x direction. In the x direction, gravity doesn't provide any force in the x direction, but T1 and T2 do. So the x component of force is the sum of the x component of T1 plus the x component of T2. Okay? And in the y, then I actually have the y component of gravity, okay, the y component of T1 and the y component of T2. And the sums of these forces are equal to 0 because there's no acceleration in this problem. Okay, in fact, there's no velocity, and so this is a situation of static equilibrium. All right, so then I can solve these two equations separately. So T1x, well, if I look at T1 looks like this, okay? And this angle here is 60 degrees, so therefore this angle down here is also 60 degrees. And T1x is this. And so T1x is just T1 times the cosine of 60 degrees with a minus sign because it points to the left. T2, on the other hand, is exactly the same diagram except the angle is 30 degrees. T2x is T2 cosine 30 degrees with a positive sign because it points to the right. And then I can solve now for the y component. T1y is this, and you can see that T1y divided by T1 is going to be the sine of 60 degrees, okay? So T1y is T1 sine 60, okay? And T2y is, well, it's the same calculation, except for the angle's 30 degrees, so it's T2 sine 30. And both of these tensions are in the y direction are positive because the component points upwards. The y component of gravity points downwards, so it comes in with a minus sign, giving us minus mg. And again, they sum up to 0. So what I have here now is two unknowns, okay, which are T1 and T2, which I don't know, okay, and two equations. That's this one, this equation here, and the equation here on the left. So I have two equations and two unknowns, and I can solve these using standard techniques. I want to eliminate T2 because I'm after T1, okay? So I'll start over here with the x part, and I'll plug in the numbers. So cosine 60 degrees is a half, cosine 30 degrees is 0.866, so I get this. And then I can solve for T2 in terms of T1. T2 is 0.5 divided by 0.866 T1, and that gives me T2 is 0.577 T1. So knowing this then, knowing how T2 depends on T1, allows me to eliminate T2 in the second equation here, and I can do that here. So I have here T1 times sine 60 degrees, which is 0.866, is equal to T2, which is 0.577 T1, right here, times sine 30 degrees, which is a half, minus mg equals 0. So now I have an equation for just T1. Okay, and I can solve for T1. So summing everything up, I get 1.15 T1 is equal to mg, or dividing by 1.15, T1 is equal to 0.87 mg. And if the question gave me what m was, I could figure out what the magnitude of T1 was. Okay. So the next question we'll do is a little bit more tricky, okay, and it involves some friction. A 45 kilogram box is pushed by a force of 150 newtons horizontally on a level rough floor. Okay, so we'll draw a free body diagram of that. You have a 45 kilogram box being pushed by 150 newton force on a level rough floor, which looks like that. Okay. If the coefficient of static friction between the box and the floor is 0.5, the magnitude of the frictional force on the box is, and it gives you several choices. So you can try and work this out before I actually do this problem. Okay. So first thing to do is to try and understand what type of problem this is. And the tricky part about this is that even though it gives you the coefficient of static friction, this problem may not necessarily be a static equilibrium problem, because you have to ask yourself, is there motion in this problem? If the 150 newton force is large enough, you can move the box, okay? So the question is, does the box remain stationary? And that's the tricky part of this question. Okay, so I don't know whether this is a dynamic equilibrium or a static equilibrium or a non-equilibrium problem. But what I do know is I can start by drawing a free body diagram. And so my free body diagram will include forces such as the force of gravity, mg, down here, or the potentially the or the normal force, n, okay? And then there will be also a force of friction, okay, which will, I'll put that there, F, okay? If the box is moving, it'll oppose the motion. If the box is stationary, it'll oppose the intended motion, okay? It'll compensate for the 150 newtons. Okay, so we have this. So along the, if I draw in a coordinate system again, x and y, then along the y direction, if I just look at y, there's no acceleration along y, so I have that n minus mg is equal to 0, or n is equal to mg, which is equal to 45 kilograms times 9.8 meters per second, which is 441 newtons, okay? So the question then is, then what is the maximum, okay? What is the maximum static friction? Well, the maximum static friction, F max, is equal to the coefficient of static friction times this normal force. The coefficient of static friction is a half, and the normal force is 441 newtons. So F max is 220 newtons, Okay. Now, one of the answers here is 220 newtons, but this is important, that F max is not the magnitude of the frictional force, not necessarily, okay? And let me explain what F max is again. So let me remind you, if I just go forward here, remember this graph I gave you in the previous lecture where I plotted the friction force on this axis versus the applied force on this axis. Okay, and there were different regimes: the static region where the velocity was 0, and the kinetic region where the velocity was not 0. Okay, and this shows you how the friction force depends on the applied force. Okay, so in this region, what F max is, what the 220 newtons corresponds to, is this point here is the 220 newtons, okay? It's the maximum static friction force that the surface can apply before the object begins to move, okay? So any applied force above 220 newtons will cause the object to move. And so what's actually happening here is your applied force is actually down here. It's at 150 newtons. So you're below the 220 newtons. And so the static friction force is able to compensate completely for the applied force. And you can determine what the static friction force is by drawing this line up to this line where Fs is equal to F, and then reading off from this graph over here 150 newtons. Okay? So the static friction force exactly compensates for the applied 150 Newton force, and you're in the region where V is equal to 0. So let me just go back for a sec. Okay, so conclusion is that the applied force of 150 newtons is less than F max, okay, which is the 220 newtons, and so the box remains stationary. And so Vx is equal to 0, Ax is equal to 0, F net x is equal to 0, and as a consequence, Fs is equal to 150 newtons and directed in that direction, to the left. Okay, so the answer then here is B, 150 newtons. Okay, now let's do this old midterm question. A 10 kilogram block is pressed against a vertical wall and held in place by a force of 150 newtons, 36.9 degrees above the horizontal. Okay, so there's your 36.9 degrees above the horizontal. The force here has a magnitude of 150 newtons, and the block is 10 kilograms, okay? There's a coefficient of static friction of 0.1, and the magnitude, it's asking you the magnitude and the direction, so two things, of the frictional force is, and it gives you these choices. Okay, so what you need to do in this problem, first of all, is ask yourself, is it a static friction problem? And there's a clue in the question. It's held in place, okay? So it's held in place, meaning it's a static equilibrium problem. And so the frictional force will exactly be determined to create an overall net zero force on this block, okay? So there's no motion. So again, our process is to draw a free body diagram, define the coordinate system, solve the force equations in x and y, and then do the math. So the free body diagram, well, there is a gravitational force acting down on the block, which is a 10 kilogram block here, okay? There is a normal force acting outwards from the wall. There is the force which we're applying, the 150 Newton force here at an angle of 36.9 degrees. And then we can define, again, a coordinate system. Up is positive along y, and to the right is positive along x. Now the issue here is what is the static friction force, and does it point up or down? So as a preliminary guess, I will take the static friction force to be up. Okay, so this would happen, the static friction force would be up if the applied force of 150 newtons, if its y component were not strong enough to compensate for the weight of the object. Okay, otherwise if the applied force, the y component of the applied force, were too great, then the static friction force would be down to prevent the object from actually sliding up the wall. Okay, so what I'm going to do then now is just assume this. If it turns out that my static friction has a negative sign, it means that I guessed wrong and the force is actually pointing downwards. Okay, so the first, just clean that up for you here. The first equation along x says that the normal force, which is positive pointing towards the right, is plus the x component of the applied force, which is F times the cosine of the angle here, with a minus sign because it points to the left, is equal to 0. Okay, and then we can solve here for the normal force, okay, because we know the magnitude of F is 150 newtons, so the normal force is 150 cosine 36.9 degrees, and that gives us a normal force of 120 newtons, okay. Then along y, we have the friction force and gravity and the y component of the applied force. So we have the static friction force, okay. We have actually maybe it might not be static friction, so I shouldn't write that. We have gravity pointing downwards, and we have the upwards pointing y component of the applied force, which is positive F sine 36.9, summing up to give you 0. Okay, so I can then solve for F. Okay, the mass is 10 kilograms, G is 9.8, and then moving F sine 36.9 to the right hand side gives me minus 150 times 36.9, which gives me that the force is 98 minus 90, which is 8 newtons. Okay, so we're not quite done yet, because we should check to see whether this 8 newtons is actually less than the maximum force, okay? Because if it's not, then the system is actually moving, which is an interesting question. So the coefficient of static friction is 0.1, so F max then is mu Sn, which is 0.1 times 120, which is 12 newtons. And so indeed, F is less than F max, and so the box in this case is stationary. All right. We'll do another problem with static friction. This one involves a movie star, Hayden Christensen, who's 70 kilograms, is rock climbing and ties his rope around a rock at the top of a cliff. If the coefficient of static friction between the rock and the ground is 0.25, what is the smallest weight? Okay, so this is what it's asking for. The smallest weight that the rock can have, okay, and still keep Hayden from prematurely ending what is undeniably a fantastic and dynamic acting career. Okay, and assume there's no friction here between the rope and the edge of the cliff. Okay, great. So how do we solve this problem? Well, there actually are two objects in this problem. There's the Hayden Christensen and there's the rock. So first we have a movie star, Hayden Christensen, and we'll represent him and calculate his free body diagram. And then we have the rock, and we'll calculate its free body diagram, although the rock is also a movie star, but we're not talking about that rock. Okay, so for Hayden Christensen, there are two forces acting on him. Gravity acting downwards. His mass is 70 kilograms, so mg in this case is 686 newtons. And then the rope exerts a tension on Hayden Christensen. There's a tension in the rope exerting a T force upwards. Okay. For the rock, we have, again, in the y direction, there is the mass of the rock times gravity acting downwards, and a normal force acting on the rock from the cliff, keeping the rock on the cliff. But for the rock, there is also a second direction. The rope, which is attached to the rock, exerts a tension on the rock to the right. And then because the rock is static, okay, the whole thing is static, there is a static friction which will exactly compensate this tension so that there's no acceleration and in fact no motion in this problem. Second thing is to define a coordinate system. Now, because we have two objects in this problem, I've written a dotted line here up the screen because it's essentially two separate problems. And so I can define two separate coordinate systems. One for the rock, okay, the usual coordinate system, and then a separate coordinate system for Hayden where it's a one-dimensional problem in y. And here I'll define down for Hayden to be positive, but it's okay if for the separate object of the rock I define up to be positive, okay, because they're two separate problems. As long as I keep that consistent or straight, that I separate the problems with this dotted line, then I'm okay. Okay, so for Hayden there's only one direction, y, and so given this coordinate system, mg is down, so it's positive mg minus the tension, and there's no acceleration, so that's equal to 0. And I can then solve for the tension in the rope. It's just mg, which is 686 newtons. So the tension in the rope is actually a quantity that also appears in the rock problem. So I've solved the Hayden Christensen problem, and now I can look at the rock problem. So in the rock problem, I can solve in the y direction and in the x direction. So in the y direction, the sum of the forces is 0 because there's no acceleration in y. So the positive normal force minus gravity, which acts downwards, is 0. So the normal force is just given by the mass of the rock times gravity. In the x direction, again, there's no acceleration in this problem. So the tension, which acts to the right and is positive, is exactly compensated for by the static friction force, which acts to the left and is negative. And so the static friction force is equal to the tension. Okay? So that would be the static friction force is also 686 newtons. Now the question asks, what is the smallest weight of the rock that can prevent Hayden Christensen from moving? And so that means that in order for this to be true, the static friction, right, of 686 newtons has to be smaller than the maximum static friction that can be achieved by this cliff face. And so the static friction has to be less than the coefficient of static friction times the normal force on the rock. All right? And so that means that if Fs is less than mu Sn, it also means that the tension has to be less than mu Sn. And N is given by the mass of the rock times G. So this N up here, right? So we have an inequality that the tension has to be less than mu s times the mass of the rock times G. And remember, the question is asking us for the smallest mass of the rock that keeps Hayden Christensen stationary. And so we can use this inequality to get that. Plugging in the numbers, 686 is less than or equal to the coefficient of static friction of 0.25 times the mass of the rock, which we don't know, times 9.8, or alternately solving the mass of the rock has to be bigger than or equal to 280 kilograms. So the smallest mass of the rock is then the lowest possible number here. MR is equal to 280 kilograms. Okay, so that's a slightly different type of problem that you could encounter in this course. Okay, so up till now we've been doing problems in static equilibrium where there is no acceleration and then also the velocity is zero. But we can now consider the case where there are unbalanced forces which can lead to the acceleration of an object. Okay, so in this case then our force balance equation is to calculate the net force, and then from that use sum of F equals ma to calculate the acceleration. So if the acceleration is non-zero, we're in a situation of what I call non-equilibrium dynamics. If the acceleration is zero, but the velocity is not zero, we're in something called dynamic equilibrium. Okay, so those are the two cases. In either case, there is motion. Okay, one is accelerated motion and the other one is constant velocity motion. Okay, so this would be v actually is a constant. And so in either case, we'll use kinetic friction. So that's the main difference. These dynamical problems will involve sliding friction, where the kinetic friction is given by a coefficient of kinetic friction, mu k, times the normal force. And a pro tip here, when drawing the free body diagram in a situation where you have an acceleration, you'll want to draw one of the axes to line up with the direction of the acceleration. It just greatly simplifies the problem. Okay, so we'll start with this quiz question, which is kind of tricky. And it's the following. A box is being pulled by a rope across a level floor, as shown in the diagram. And the question is then, what is the tension in the rope? And the key point here in the diagram is you see that there's an acceleration. So the box is actually accelerating at 1 meters per second squared. So if the box is accelerating in this direction, then there's going to be a force of kinetic friction acting to oppose the motion, acting on the box. Okay. All right, well, we start by drawing a free body diagram for this situation and putting in a coordinate system. And so our acceleration is to the right, and so we can align, say, the x coordinate with the direction of the acceleration. So right is positive, and in this case the y coordinate up is positive. And then for the box, gravity acts on the box, the normal force from the floor acts in the opposite direction on the box. The rope provides a tension force acting on the box at 60 degrees to the horizontal. And there is a kinetic friction force acting to oppose the motion of the box. Okay? So, in the x direction, I balance the forces, although now the net force in the x direction is given by m times a, not 0 anymore, because the acceleration is now 1 meters per second squared. And so in the x direction, I have positive the x component of tension, which is t cosine 60 degrees, and then I have a minus F, which is the kinetic friction, which is acting towards the left, so it comes in with a minus sign. In the y direction, on the other hand, I have that the positive normal force is compensated by the downwards force of gravity and also by the upwards y component of tension, which is t sine 60 degrees. So if I draw in the tension here, this is Tx, this is Ty, and this is 60 degrees. Okay? Now in the y direction, there is actually no acceleration, and so I can simplify this by sticking this, well, this is equal to 0. So that's why it's so important to choose your coordinate system where, say, one of the directions aligns along the acceleration, because you know then that the other direction, in this case y, has no acceleration along it. Okay, so I have now two equations. I can plug in for the kinetic friction here. So I just plugged in mu n for the kinetic friction in the x equation. And here I've solved for the normal force n. But I still have, again here, two equations in two unknowns. Okay, so my unknowns here are the normal force and tension. The question asks me for the tension in the string, so I want to eliminate the normal force and solve for the tension. And so I can do that here because I know the normal force in terms of the tension from this equation here, and I can substitute that into here and then solve for the tension. So doing that, I get t cosine 60 degrees minus mu times the normal force, which is mg minus t sine 60 degrees, is equal to ma. And then isolating t, I get t times cosine 60 plus mu sine 60 minus mu mg, coming from here, okay, is equal to ma. And then I can solve for t. Okay, so moving the mu mg over to the right-hand side, inserting a plus sign, ma plus mu mg, and then dividing through by this factor which multiplies t cosine 60 plus mu sine 60. Plugging in the numbers, I get 10 for the mass, 1 for the acceleration, 0.5 for the coefficient of kinetic friction, 10 for the mass, 9.8 for g, divided by 0.5 for the cosine of 60 degrees, 0.5 for the coefficient of kinetic friction, and 0.866 for the sine of 60. Putting that all in, I get 63.2 newtons, which is answer D. Okay, so that is an example of a non-equilibrium dynamics problem where the acceleration is non-zero. And let's do one more example here. So getting back to Hayden Christensen, unfortunately it's actually started to rain, and Hayden Christensen hasn't made much progress since we last saw him. And I believe this is referring to his rock climbing. And so the 280 kilogram rock that we had before starts slipping on the slippery cliff. And Hayden begins his plummet at a constant acceleration now of 1.5 meters per second squared. Okay, so again, Hayden 70 kilograms and the rock is 280 kilograms. What is the coefficient of kinetic friction between the rock and the wet ground? Okay, so we'll want to know the kinetic friction force, and the kinetic friction force is the coefficient of kinetic friction times the normal force. So what I need to know is the normal force and the kinetic friction force in order to solve this problem. Okay, so setting this problem up again, well, it's the same free body diagram essentially. For Hayden, there's a tension acting upwards on him and gravity acting downwards. For the rock, the rope exerts tension. There's now a force of friction, but it's now kinetic friction. And in the y direction, there is the mass of the rock and the normal force. Okay, so it's now kinetic friction. The difference here, though, now is that Hayden is actually accelerating downwards and the rock is accelerating to the right. So we have to take that into account in the force balance equations. Again, assigning a coordinate system to the rock and a separate coordinate system to Hayden, the same ones as we used before. We can then solve for Hayden's problem, first of all, that the sum of forces in the y, which is mg, positive mg down, negative t up is now not equal to 0, but it's equal to m times a, because now Hayden Christensen is actually accelerating downwards. Okay, so I can solve for the tension. It's mg minus ma. I'm given both of these. G is 9.8, a is 1. So it's to the mass of 70 kilograms times 9.8 minus 1.5. A is 1.5 meters per second squared. And so now the tension in the rope is only 581 newtons. So the tension is less than mg, which is why Hayden Christensen is actually accelerating downwards. For the rock, I can solve first of all for the y. Okay, there's no acceleration in the y. Okay, and so the normal force is just again the mass of the rock times g. Okay, and remember that mr in this problem is now 280 kilograms. So I know the normal force. But I also have to solve for the kinetic friction force, okay, in order to get the coefficient of kinetic friction. So along x, I have two forces acting. I have the tension force acting to the right and the kinetic friction force acting to the left. And now there is a non-zero acceleration of 1.5 meters per second of the rock, okay, assuming that the rope doesn't stretch. So isolating now for Fk, Fk is the tension, which I know, the mass of the rock, which I know, and the acceleration, which I know. And so I can actually solve for Fk. And then I also know that Fk, the kinetic friction force, is the coefficient of kinetic friction times the normal force. And I know the normal force. So I can start to plug in the numbers. So the tension in the rope of 581 newtons minus the 280 kilogram rock, which is accelerating at 1.5 meters per second, is equal to the coefficient of kinetic friction times the normal force, and the normal force is the mass of the rock, 280 kilograms, times 9.8 meters per second, the gravitational acceleration. I can solve for the coefficient of kinetic friction, and it is 0.059, which incidentally, remember the coefficient of static friction was 0.1, and here is a case where the coefficient of kinetic friction is less than the coefficient of static friction, which is not surprising because a wet, slippery rock is, well, slippery. Okay, so I'll just summarize what we've done. These examples, we've examined three situations: static equilibrium, dynamic equilibrium, and non-equilibrium dynamics. In fact, we've examined these two situations in detail. So for static equilibrium, the object is not moving, so the velocity is 0, and also then the acceleration is 0. And so the sum of the forces, the equation you use is that the sum of the forces is 0. And in this case, the static friction opposes the intended motion, and so we'll use static friction. And the key point about static friction is the static friction is determined by the condition of force balance, that is, this condition. And as long as this static friction, so determined, is less than this maximum force, which is determined by the normal force and the coefficient of static friction, then the object remains not moving. Okay. Now in a dynamic equilibrium problem, the object actually is moving, but the velocity is constant. Okay, so this is a v equals constant situation, which is also a zero acceleration situation. So then the sum of forces is actually still equal to 0, except for now the object is actually moving, and so instead we'll use kinetic friction. And we'll use the fact now that the kinetic friction is now given by the coefficient of kinetic friction times the normal force. Okay? So it is independently given by this. And then finally, the situation of non-equilibrium dynamics is where the acceleration is not equal to 0. And so now we have to use the sum of the net forces in at least one direction is equal to mass times acceleration. And again, there is motion in this problem, and the friction will oppose this motion. So we'll use again the formula for the kinetic friction. So these are the types of problems that we get in this course. And we spent some time doing these non-equilibrium dynamics problems, and we spent some time doing these static equilibrium problems. And I didn't actually do a dynamic equilibrium problem where there's a constant velocity, but I'll leave you with this problem for you to do by yourselves. This dynamic equilibrium problem: a light cord is passed around a frictionless pulley and connected to two masses as shown, with M2 pulled by a constant horizontal force F. The coefficient of kinetic friction is between M1 and M2 is the same as that between M2 and the horizontal surface. What is the value of the coefficient of kinetic friction if the blocks are to move with constant speed? So the constant speed means that it is a situation of dynamic equilibrium. Okay, thank you very much.